You are seeing my screen? Okay. Not able to see the screen?
Visible, sir.
So yesterday in the last class, a lot of people are absent. So we just that is a physical class, I think. A lot of people are absent, but I just gave a recap of what we did. So we are doing on problems. So I think this will be the last problem before we go to the next chapters. So for a parallel reactions, you need to understand how we can do the contacting patterns. Right? This is a qualitative and quantitative analysis. Qualitative, we discussed about high concentration favors higher order reactions. Low concentration favors lower order reactions. Right? So qualitative and quantitative analysis, we are discussing about psi and pi. Psi is you can see here psi and pi. I'm talking about psi and pi. Psi is the instantaneous fractional yield, which tells it is moles of R formed by moles of A reacted, and pi is the overall. So all R formed by all A reacted. Right? So we need to calculate this fellow. That fellow is instantaneous fellow, and then try to calculate the overall for a different experiment, for a different reactors. For a PFR, this is the calculation of pi p with respect to instantaneous yield. You get an integral. But for a MFR, your total is nothing but individual or instantaneous at the final value. Using these two relations, we can calculate, if you know one particular pi p for a plug flow reactor, you can predict what will be the total yield in MFR by using these relations. These four are very important. This is PFR, MFR, and then doing from one to the another one. The another one which is most important is if there is staged reactors, then this is the formula to calculate the staged reactor, that is reactors in series. And final thing is whatever you are having, either plug flow or a mixed flow, you are calculating the overall, but you need to calculate what is the R, that is the desired concentration final, that it will be phi, that whatever you calculated into the concentration change. So these five formulas are very important. This formula is important when you are having different reactors in series. These two are very important for a plug flow and a mixed flow. And if you want to convert one form to the other form, this particular thing is very essential. Remember, for a PFR, you get integral, and for MFR, you won't get that integral. That is the basic thing. So for this to do, you need to calculate this instantaneous yield, right? So that is what we will do in the problem. This problem is a very important, a lot of times they ask this problem. Please write this problem. Last class, some of you might have written in the class. Those people who are absent, you can write it. I'll just read it. Consider and the aqueous reaction A plus B gives R and S, K1 and K2. This is the desired. So this is the rate expression. dCr by dt is 1, Ca power 1.5, Cb power 0.3 mole per liter minute. This is the unit for dCr by dt. That is the formation of R. Like that, formation of S is 1, Ca power 0.5, Cb power 1.8 mole liter per minute. So he is asking about 90% conversion of A. Find the so A conversion is 90%. Find the concentration R. R is asking you CR, the CRF, that is final. In the product stream, if equal volumetric flow rates of A and B are there, So fed to the reactor, each stream is having 20 mole per liter. So he's giving you the concentration of the stream and equal volumetric flow rates. So he's asking you to calculate the concentration of R of this desired product if this reaction is happening in plug flow or a mixed flow or any one of the schemes which we showed in the previous one, that is a combination of a plug flow and a mixed flow and all, right? So we'll do that first. We need to do the instantaneous yield. So we will get this instantaneous yield phi R by A, that is instantaneous yield of R divided by A, how much R is formed divided by how much of A is reacted. R is formed is DCR. How much of A is reacted is nothing but the formation of R and formation of S, because both R and S is formed from A. Therefore, how much A is reacted is nothing but how much A is formed, R is formed, and S is formed. So they gave how much this formed, right? K1 Ca power 1.5, Cb power 0.3 divided by this particular thing. So here K1 is K2 because you are not changing any temperature. And one more is Ca and Cb power 0.3. If you take it common, it gets cancelled out. So numerator you take something common and denominator you take something common. Then you are left with Ca by Ca plus Cb power 1.8 because you are taking Cb power 0.5 common out. So Cb power 0.5 and if you take Cb power 0.3 here, then Cb power 1.5 will remain, right? So this is the instantaneous yield. From this, you need to calculate the concentration of R for a 90% conversion of A in plug flow reactor. So let us choose the plug flow reactor. For a plug flow reactor, noting the concentration of the reactant E stream in the combined stream is Ca0 is Cb0 is 10 mole per liter and Ca is Cb everywhere because that is what he gave here. Each stream is having a same concentration, volumetric flow rate. But here 20 mole per liter is there. But here he is taking 10 mole per liter because each one is having the same thing. Therefore, when you are adding these two streams, so two streams, it will be divided by 2. Am I right? Because same volumetric flow rate. It gets diluted. That is why Ca0 and Cb0 is 10 mole per liter. So pi p, that is the overall yield, is -1 divided by Ca0 minus Caf into pi dCA. This is the expression to calculate the overall fractional yield from instantaneous yield. Instantaneous yield is this. So substitute that. So Ca0 is 10. Initially it is 10. Caf is 1 because 90% conversion is required. 90% conversion starting with 10, then you get as 1. Am I right? For 90% conversion. So that is why Cf is 1. Integral, again, 10 to 1, Ca0 minus Caf. Psi is nothing but Ca by Ca plus Cb power 0.5 into dCA. Correct? So Ca is Cb. We know that is nothing but same concentration, so equal volumetric flow rates. So Ca you can write as Cb. That is what we are doing here. So you take common Ca outside and 1 divided by 1 plus Ca power 0.5. So you need to calculate the integral for this. The differentiation of this is this. Therefore, this will become ln. That is what he is doing here. So let Ca power 0.5 is x, because this is 0.5. Therefore, Ca becomes x square, dCA becomes 2x dx. This is the regular way of doing the what is this integration, am I right? Because this is root x. Then you put all that. Then if you do the calculation, 1 by 9 because 10 minus 1, 1 power root 10 because you are substituting the, because Ca is you are putting x, therefore you have to substitute the limits also. 2x dx by 1 plus x. So this is nothing but ln. That is what you are putting here. And if you substitute all the limits, you are left with 0.32 pi p. So pi p is 0.32. but he's asking you the final conversion. Final conversion is nothing but CRF is pi into the concentration difference. That is what I just showed you here. I told you this for any reaction. This is very important. The CRF is pi into concentration difference. Concentration difference is 10 minus 1. Pi is nothing but pi of the plug flow. That is what you are putting here. So pi of plug flow is 0.32 into concentration difference is 9. So 2.86. You can calculate CSF also if you want, because he is asking only CRF. But if you can want to calculate CSF also, you can calculate. CSF is nothing but 9. This is nothing but the pi p. 1 minus pi p will give you CS, right? This is for pi p for R. 1 minus that it will give you for the another reactor, the another product. 1 minus this. Therefore, 6.14 will be the concentration of S, and 2.86 is the concentration of R. So like this, you have to do for a mixed flow also. So for a mixed flow, again, you have to take the mixed flow expression. So this is the thing what you are getting. Ca naught and Cb naught is 20 mole per liter. So once it is added here, then your concentration drops, because Ca naught, there is no Ca naught here, but equal moles is being added. 1 liter and 1 liter, it becomes 2 liters. So in 2 liters, your concentration will be half of it. Remember it? That is why you are getting this half. So CAF and CBF is 1, because 90% conversion is required. So CRSF plus CSF becomes 9. Remember it? Because this is 1 in the sense, this becomes 9. The total becomes 9. That is why you are putting that. So we'll go for mixed reactor. Mixed reactor, again, we have to take that equation. Ca is Cb. Pi m is R by A. That is nothing but pi at exit. What is the exit? Pi at exit. What is that pi? Pi is nothing but this. What is the pi? Ca by Ca plus 1 point. So Ca also you can calculate, you can cancel out, because Cb is Ca. Therefore 1 by 1 plus Ca power 0.5. That is what you are putting. 1 by 1 plus Ca power 0.5. Ca at the exit. Exit is nothing but Ca at the exit, right? At the exit, Ca is nothing but 0.1. So substitute 0.1 here, and then you can calculate 0.5. So here your pi p is 0.32, but pi m, that is a mixed reactor, it is 0.5. So once you calculate pi, you can calculate CRF. CRF in mixed flow. CRF in mixed flow is nothing but pi into the concentration difference. Pi is 0.5. Here it is 0.3 you are putting. Concentration difference is 10 minus 1, that is 9. So 4.5 mole per liter you are getting. Whereas CSF is 9 into 1 minus 0.5, that is 4.5 mole per liter, right? So both are same here, especially in a mixed reactor. So this is the physical representation. This is 20 moles, 20 moles it is given in the problem, but both are mixing inside, therefore the concentration drops. So how much it is dropping? This is 1 liter, this is 1 liter. In 2 liters, you are having 20. In 1 liter, 20 by 2, it is 10. So CAF and CSF is 1, CRF and CSF is 9. This is how you have to do. And for the third one, plug flow A and mixed flow B. Now this combinations which is given in this particular first problem, that is what you have to see. What are the 4 combinations? These are the 4 combinations. One is plug flow reactor, but B is intermediate, that is high A, low B. Like that, this is low Ca and Cb low, Ca and Cb high, and then this particular, these two already we studied, we did now, right? Ca and Cb in a plug flow reactor we studied, we already did, and Ca and Cb in CSTR also we did. So these two we need to do now. That is what they are doing in this problem. Yeah, for this, for a plug flow A and mixed flow B. So plug A is plug and B is mixed. So this is 20 moles and this is also 20 moles. That is what he is giving in the problem. So A will happen to be here once A is going here. So B is not just added here. Therefore, B becomes 1 and CA naught becomes 19 because these two is being added 20. So 20 minus CB is 1. Therefore, 19 and 1. So CRF and CSF is 9 because 90% conversion is required, and CBF is 1 everywhere because you are intermediately adding only 1, right? See, assume that CBF is 1, then CAF will be 19 because both are being added here. So total is 20. So if you assume CBF is 1, so CAF will be 19. That is what. So if you see pi, pi r by a is minus 1 by CA naught minus CAS into integral CA naught to CAF pi dCA. So CA naught is 19 now, CSF is 1. So if you substitute CA by CA into 1 plus 0.5 dCA, you need to do the integration for this and substitute the limits. You are left with 0.87. So this is a very good combination because pi is you are getting very high. Therefore, CRF will become as this pi into the concentration difference is 10 minus 1, that is the initially 10 minus 1, that is 9, 7.85 mole per liter, and CSF will be 1.15. So to summarize, you know that for a plug flow reactor, pi by R by A is 3.2. And for a mixed reactor, your overall yield is 0.5. But for an optimum thing, this is the optimum generally because you need to have very high of A and low of B. For that, optimum is 87. You can do the other way around also if you want. Then, but still he is not doing here. That is why he is telling that it is optimum. So CRF is 2.86. If I use a mixed reactor, it is 4.5. But if I use a plug flow reactor with intermediate B, then I get CRF is 7.85 mole per liters. This is a very important problem. And one more problem I think we'll do. Any doubt in this problem? So here one important thing is how to calculating this. Pi p, especially for plug flow reactor, you need to do the integrals. You need to do the integrals and substitute the limits. For a mixer reactor, no need of integral. Just substitute that final concentration in that instantaneous equation. Then you can get your overall. Yeah. Then we go for one more problem. One more. This is one more problem. Lot of times they ask this problem in the exam. Please try to do this problem. Right, lot of times he asked in this this particular thing in the exam. So he's giving three products here. So here see, to see a single reactor gives a best combination. So simplest case, the parallel decomposition of A, Ca naught is 2. Initially concentration of A is 2. A is giving R, A is giving S, and A is giving T. So the formation of R is 1. The formation of S is 2Ca. The formation of T is Ca square. You see any question paper in CRE1 in third unit, almost for every two question papers, this problem will be asked. This is a worked out problem. Not only worked out, even in the exercise problems also, similar type of problems they will ask. So he is asking you find the maximum expected CS. So CS is the desired, whereas R and T is undesired. You want only the S combination. S is there. So he's asking how much is the maximum CS for this isothermal operation. If you are using a mixed reactor, how much you will of S you will get, and if you use a plug flow reactor, how much S you get, or if there is a reactor of your choice, you take any reactor of choice, and if unreacted A which is unreacted can be separated from the product and return to the feed at Ca naught is 2. So what he's telling is he's having a recycle reactor here. The unreacted thing is separated from the product and then sending back to the reactor. The reactor can be of any choice, of your choice, mixed or plug flow. So this is a very important problem. A lot of times they ask this problem. You can check in the question papers. Already I uploaded a lot of old question papers in the LMS. So you can see that particular this particular question there, right? So for this, first we need to calculate the psi, that is the instantaneous, and then we need to calculate its overall, right? So he's asking maximum. So how you can get the maximum? If you can calculate the psi and then differentiate this psi equal to 0, then you can get maximum or a minimum. But how you can know it is maximum? Then again you have to do the second differential and then substitute that value. Then if your value is negative, then it is maximum. If it is positive, it is minimum. That is just school stuff. Where is the maximum? Where is the minimum? Right? But you know that the differentiation of it will give you either a maximum or a minimum. So we to calculate that. Yeah, to calculate that, we need to calculate the psi of S by A. Why S we are putting? Because S is what is the desired. So this is the desired. So S by A is nothing but how much of S is formed divided by how much of A is reacted. The A is reacted is nothing but DCR plus DCS plus DCT. So if you substitute the rates of what he gave, 2Ca divided by 1 plus 2Ca plus Ca square. This is nothing but 1 plus Cax whole square, because 1 square plus Ca square plus 2Ca. So instantaneous yield is getting as 2Ca by 1 plus Ca square. For this we need to maximize. So maximum, it will happen for this somewhere. You need to find out that maximum concentration. How to find out? Differentiate this with respect to Ca and then equal to 0. Right? So that is what I am doing. Phi by dCa, that is differentiation of this, is differentiation of 2Ca by 1 plus Ca whole square is 0. If you do that, if you solve this, you get the phi value. The phi value at 0.5, phi value is 0.5 at Ca as 1. At Ca1, you have this maximum of instantaneous yield. That is the value which you are getting from this. Or what you can do is you can draw with different Cas and pi of Sa versus Ca you draw. Take Ca values from 0 to 2, some value you take and then calculate and then try to draw a graph. This is how you get. This is how you get for a MFR at a 0.5. That is what he is giving at 0.5. You take the rectangle. This is the area under the curve, area of a rectangle. And for a plug flow reactor, you know that area under the curve will give you the value. And for anything, for any of the reactor of your choice, you need to have Ca at 1, because that is where the maximum, because your curve is going up and then decreasing. So you need to keep this particular value. At this particular value, you are having the maximum of R. That is what you can get from the graphical also, or even from the analytical expression which you are doing here, right? So for a mixed reactor, that is what he's asking you. For a mixed reactor, we'll see. For a mixed reactor, most of S formed when the triangle under the phi curve has a larger value. So if you want S more, the triangle, this rectangle should be more, right? Rectangle should be more. When this rectangle will be more, already we discussed the maximization of the rectangle. This rectangle will be more when the diagonal of this rectangle is equal to the diagonal, not diagonal, this is the slope, tangent of this particular curve. If the tangent is parallel to the diagonal of this particular, what you call, mixed reactor, then you can get the maximum rectangle, right? So that is what he is asking. He is giving most of S is formed when the rectangle under this has the largest area. How, when it will have largest area? The required condition can be found either by graphical maximization of the rectangles or analytical expression. Since the simple explanatory equation is there, we use the later approach. So you can use 10 equation and 13 equation. This is the 10th equation, 13th equation to calculate CSF is nothing but psi of CS into the concentration change. Psi is 2Ca by 1 plus Ca square. Concentration change is Ca naught minus Ca. So this particular thing should be maximized. Then either you can go for differentiation and equating and then calculate the Ca. This is what you can get by analytical approach. Or you can do a graphical approach. This particular thing you try to draw. You take some value of Ca and then calculate this pi by Sa and then draw and then try to maximize this rectangle by putting this diagonal is equal to that is the slope of this diagonal is equal to the slope of this particular tangent. That it will happen when this diagonal, what you draw for this particular rectangle, is equal to the parallel to this particular tangent, right? This is just a school stuff which how to maximize the rectangle, right? So that is what you are getting. If you equate here, CSF will be 2 by 3 at CAF is half, right? So CSF, what maximum you get is 2 by 3. If you use a plug flow reactor, again the production of S is maximum when the area under the curve of phi is maximum. That is what you are seeing here. When this particular area is under the maximum, then you get S maximum. So how to calculate this area under the curve? That is what again you are doing. CSF is minus Ca naught CSF into what you call this instantaneous yield into dCA. So CSF is 0 to 2, CSF final is 2, then 2Ca by 1 plus Ca square dCA. So we need to calculate the integral for this, and for if you do that, CSF will be 0.867 at CAF is 0. So CAF is 0. So CAF is 0 in the sense entire A is reacted. When the entire A is reacted, you are getting the CSF as maximum. Here you are getting only 0.6, but here you are getting 0.8. So if you use one more combination, that is for any reactor with a separation, then since no reactor leaves the system unconverted, what is important is to operate the condition at high fractional yield. So high fractional yield will come at Ca is 1. That is what we discussed in this particular thing. So Ca at 1. So Ca at 1 and phi A is 0.5. Then we can use a mixed reactor operating at Ca1 and then leave 50% of A forming the product S. So here if you see entire thing, 0.33 for the MFR, the moles of A, S formed by moles of A fed is 0.33 for MFR, 0.43 for a PFR. And if you are using any recycle stream, especially for a MFR, you can get 0.5 concentration of S, right? So thus a mixed reactor operating at a conditions of highest phi with a separation and a recycle will give you the optimum value of S. That is the desired component, right? So this problem is very important. Somehow you try to do once more time. So based on this, they'll give you a lot of problems in the exercise. Just I'll show you that. This is one more combination. You can see the exercise problem. This is, you can see this problem. This is one more problem. This is the one more problem. This problem also they asked a lot of times in the exam, 7.7. So even 7.7, you can see here in some 7.8, 7.9, you are using these values. So try to do this 7.7. 7.7 is R and S is given. The formation of R is given. Formation of S is given. He is giving the feed is Ca0 is 1. Cr0 is 0 and Cs0 is 0.3. Initially, there is 0.3 of S. Enters two mixed reactors in series. So this particular reaction is happening in two reactors in series, which is having tau1 and tau2. Knowing the composition in the first reactor compositions also is giving. Find the composition leaving the second reactor. So this problem is also I'll show you here. This is the solution book which I circulated to the Yamini. I think you can circulate to that student. This is 7.7. A is giving R and A is giving S. RR is K1Ca square, RS is K2Ca, and two reactors are there, mixed reactors. So he is giving you initial compositions of A, R, and S, and he is giving you after this reactor also combinations. What is the conversion? What is the concentration? He is asking you what is the concentration at the end. So tau 1 is given, tau 2 is given. So for a mixed reactor, you know that tau 1 is CR1 minus CR0 divided by KCa square, because you are writing for R is the desired product. So from this K1 you can calculate. K1 is the rate in this because tau is given. So based on that 0.5, like that tau 1 you can tau 2 also you can tau 1 you can calculate. Tau 1 is 0.5. If you substitute 0.5 here, then we can calculate K2. K2 is 0.4, K1 is 0.5 and K2 is 0.4. Like that you can do for the second reactor also tau 2. Then you can calculate tau 2 is Ca1 minus Ca2 by K1 Ca square plus K2 Ca. Ca1 is given, Ca2 you need to calculate. Tau 1 you already calculated or already given here. So based on that you can calculate Ca2. Like that you can calculate the rest of the things CS2 and CS2. That is what is giving CR2 and CS2. So go through this solution manual and with the problems of this entire problem. These entire problems are very important because parallel reactions is to understand it is a bit tricky, especially to calculate the what do you call that instantaneous and overall yield. That's a bit tricky. Please try to do some 2-3 problems so that you will understand much better. This is one more problem which they ask. Consider this parallel combination. This is the same which we determine the maximum concentration if it is a plug flow or if it is a mixed flow. Right? So 7.14 R is the desired product, S is the desired product, and T is the desired product. So he's asking for a plug flow or a mixed flow. If R is the desired product, what is the combination? And if S is the desired product, what will be the thing which comes from plug flow and a mixed flow, and even T. So try to do this problem also is so that you feel comfortable with the equations, right? So I gave not only the problems what you need to do, I am giving you the solution book. So try to go through these solutions. It will be very useful, especially how they solved it. So from the solutions, at least you can learn more. And if any difficulty you are finding it, please let me know, right? So shall I continue with the next one, or any doubt you can ask me, or we can go for the next thing. Yeah, anything? Yeah. So here there is multiple reactions in series. We did with parallel. There can be multiple reactions like this also. This is a series reaction. Again, this is the series parallel combinations. You can see it, this series and parallel you call the system as Denby, because this scientist Denby, he gave a lot of what do you call the formulas for this kind of series and parallel combination. These are all only for irreversible reactions, and if it is a reversible reaction, it becomes still very difficult. It's not that easy to do it, right? So Denby reactions is not there in your syllabus, so that you can understand or read when you study MTech or something like that. But series reactions is there. That is what we'll go for the next one. Yeah. Parallel, any doubt, man? Any doubt in parallel? If no doubt, then we can go for a series reactions. Series reactions is very important. Again, here qualitative and quantitative analysis will be coming, right? Yeah, shall I proceed? Yeah, ma? Shall I proceed, ma?
Yes, sir.
Yeah, I think. So in series reaction, we know that A is giving R and R is giving S. So K1 and K2. So we can write the rate expression for disappearance of R, the net rate of formation of R, and the formation of S. So rate of disappearance of A is minus dCA by dt is K1 Ca. formation, net formation of R is nothing but how much it is formed minus how much it is being disappeared. So K1 it is formed and K2 is disappeared. So that is why I'm writing as net rate of formation, because we want the formation of R. So that is why formation minus the disappearance. Then RS is the formation of S. So dCs by dt is K2Cr. So when you are having this kind of systems, again you know that R will be maximum somewhere. We already derived what is the at what point R will be maximum, right? So that derivation will take into picture. This derivation was already done in first unit, because you are taking dCr by dt plus K2Cr minus K1Ca is 0. Then you need to do the integral for this, that solution. Already we derived in the previous units, right? So before going to that quantitative treatment of it in terms of the expression, let us understand the qualitative, what is happening here, right? So here, I am imagining there is a mixed reactor. There is a mixed reactor where there is a stirrer which is being stirred, and the reaction which is happening is A is giving R and giving S, right? So you are assuming that this reaction is happening in the presence of some light. Imagine that this reaction is happening in the presence of light, right? So A is being present here. So in presence of light, this R is formed and S is formed, and it is getting mixed. So how will be the combination? How will be the concentration of A? So I'm drawing concentration versus time. So imagine that this reaction is reacted only in the presence of light. So when there is no light, time t is 0. When you on the light, the reaction is happening. This is the time. So with the time, what happens? As the light switched long back, the reaction will start. Therefore, A concentration will come down. We know that R combination R is formed. So R will be formed as the A is less. You know that R will have a maximum value. And then the formation of R will decrease, because R will form, then again S is going to be formed. Therefore, the formation, net rate of formation of R will be less, right? That is why it is coming down. And if you see the concentration of S, it goes on increasing, right? It goes on increasing. So you get A combination, A concentration going down, R concentration going up, whereas R concentration, sorry, I made it wrong. A concentration is going down, S concentration is increasing, and R concentration will go on increasing at a point, then starts to decrease. When R is starting to decrease, the combination of that is the concentration of S will go on increasing, because R is disappeared to give you S, right? This is the concentration time diagrams. If the content of the beaker are irradiated uniformly, if you are uniformly irradiating this particular thing, then this is the curves we get. But if you want your R to be maximum, if you want your R to be maximum, you don't want this kind of reactions like this setup. How can I make this R more? Here, if you see this kind of reactions, if you leave, if you put irradiated here, then S also will be more. S is undesired, R is desired. So how can I make S less and R more? Yeah, any idea? This particular thing itself, what changes you will make so that I get only R more than the S? Yeah, any idea? How can you maximize this R, minimize this S? But if you are putting this combination like this, you are maximizing R, not maximizing, sorry, you are maximizing S, not R, because R is maximum and then decreasing, right? You don't want S formation. Yeah. What changes I can make in this so that my R combination, R concentration is more than the S combination, S concentration. Yeah. So for a series kind of reactions, yeah, I know it is difficult for you to visualize. For a series kind of reactions, your reaction, that is entire A should not be reacted at a time. If your entire A is getting reacted at a time, then what will happen? R is being formed, R is being disappeared to give you S. So if you use like this combination, you definitely get S more than the R. So you don't want that to happen. So what we do here is, now you see here, the same reaction, this the same reaction. Yeah, I think here, I made it wrong. You want S more, not the R combination. So if you want S more, then what you do is, you can see here, I take one small, I'm adding this A here. Then what will happen is, I won't irradiate here. Then what will happen? I'm pumping some amount of A and then into a glass tube where the reaction is happening in presence of this light. Then what will happen? A is giving R, R is giving S, right? So that particular small R or S is again circulated back. Again circulated back. So in this process, what will happen is, you are not irradiating A alone. You are not irradiating A. You are taking only small part and then irradiating and then sending back. In this process, what will happen is, definitely A value will be coming down, but R value is not being formed because only small part is there. Therefore, the entire reaction will happen yes, and then instead of R which is being formed, you can maximize the concentration of yes, where the R value will be very less. This is how it will be done, especially for a series reaction. The concentration time curves for the contents of a beaker if only a small portion of the fluid is irradiated at any instant. I'll just show you that. Let me go to that particular thing, what is being given. Yeah. So this is the combination which I'm talking about. So let us see what is the combination here. So I'll just read, go through it. Consider the following two ways of treating a beaker containing A. So this is one way, and the another way is this. A gives R gives yes. This is one more way, right? So here it is being irradiated. All the A is irradiated. You know that this reaction is happening in terms of in the presence of light. So here only some of A is being irradiated and then recycled. So he is comparing these two. Consider the two ways of reacting. First, the contents are uniformly irradiated. The second, a small stream is continuously withdrawn from the beaker and irradiated and returned to the beaker. The rate of absorption of the radiant energy is the same in the both cases. The schemes are shown. During the process, A disappears and the products are formed. Is the product distribution of R and S different in these two beakers? Let us see. The first beaker, the contents are being irradiated all at a time. So here the contents are irradiated all at a time. Therefore, the first bit of light will attack A alone because only A is present at the start. The result is the form R which is being formed. With the next bit of light, both A and R will be compete because A and R tries to take the energy, light energy. However, A is large because concentration of A is very huge. So it will preferentially absorb the radiant energy to decompose to form more R. Thus, the radiation concentration of R will rise while the concentration of A will drop. This process will continue until R is present in high enough concentration so that it will compete favorably with the A for the radiant energy. When this happens, a maximum R concentration is reached. After this, the decomposition of R becomes more rapid than the rate of formation, and the concentration is dropped. This is what we already discussed in the previous classes itself. So what will happen here? If this you are taking this combination, you are not having any R form. Why R is not formed? I'll just see here in the alternative way of treating it. a small fraction of the beaker's contents are continuously removed, irradiated, and returned to the beaker. This is what the combination I'm talking about. Although the total absorption is same in the both the cases, the intensity of the radiation received by the removed fluid is greater. It could well be if the flow rate is not too high, the fluid being irradiated reacts essentially to completion. So what does he tells you is this? Here the light is being irradiated for entire A, but here the entire light is same, only a fraction of A is being irradiated. Therefore, what will happen? There won't be any intermediate because it goes for a complete conversion. That is what he is giving, because the amount of A is very less and the total light is being absorbed by small quantity of A. Therefore, it immediately forms S, not R. So this is the way which you want to suppress in between the reaction. You can contact this way. That is what he trying to give. Again here. The received by the fluid is greater, and it could well be if the flow rate is not very high, the fluid being irradiated reacts essentially to the completion. Again, it depends on the flow rate with which you are pumping here. If the flow rate is very high, the time spent by this molecule inside will be very less. So if the flow rate is normal, then more time it will spend and more light it will absorb, right? So in this case, A is removed, S is returned to the beaker. So here, essentially what is being returned is S only, because A is completely converted to S. Therefore, no R is being formed here. So intermediate, you are suppressing it. So that is what he is giving, while R is absent. This progressively shows. So two methods of reacting the contents of the beaker yields different product distributions, represent two extremes in possible combination. One with a maximum possible combination of R and one other with a minimum or no formation of R. So it depends on if you want R more, you go for the first one. But if you want S more, so you go for this combination. That is what is giving. So for any qualitative analysis for a series reaction, for a irreversible reactions in series, the mixing of the fluids of different compositions is the key to the formation of the intermediate. It's very important. For a irreversible reactions in series, the mixing of fluid is very important of different compositions. The maximum possible amount of any and all intermediates is obtained if the fluids of different compositions and at different stages of conversions are not allowed to mix. Here what is happening is different compositions and different conversions are being mixed. But here what is happening is it is not being done. Only A is there, A is pumped, or S is being written. So this is the mixing is very important, and mixing of what fluids is also different compositions and different stages is also very important. That is what he will show you in one problem. Just to go through this problem, in the next class we can discuss about more about this particular problems, right? So qualitative treatment in qualitative treatment of series reaction, the mixing is very important. That is what it tells. Whereas in quantitative, it will give you in terms of the equations, which we already derived these equations. For this particular thing, for a batch reactor or for a CSTR or for a PFR, you need to calculate CR max by CR naught, because this expressions is you are doing for a batch reactor. For a batch reactor is this, or even for a plug flow reactor also you can use the same design expressions. For a mixer reactor, you need to do the derivation. That we will do in the next class. Yeah, that is what even in the PowerPoint presentations also I might be showing you. So here is important here, right? So favorable contacting, that we will see in the next class. Then the qualitative treatment we'll see in the next class. This derivation is very important. This is the derivation already we derived. The same derivation we'll do, and then go for the next particular thing. Till this derivation we already derived in the first unit. So that we'll see in the next class. If there is MFRs, how to calculate it, and if there is a PFR, how to calculate in series reactions. I'll stop here. Yeah, any doubt, let me know. Lot of 26 is present. One second. I already gave the attendance there. 26. How to mark your presence? 26 is present. Okay, good. Then anyone else present? 305 also present. 305 also present. Okay. Anyone else, ma'am? Here I am seeing the chat. 34 is also present. 34 already. Yeah, 34 is present. I gave. 16 is present. That's what you are putting in the chats. 16 is present. Yeah, okay. Yeah, anyone else, ma?
21, sir. I
20.
joined 5 minutes late.
Okay, no problem. 21. Yeah. Anyone else? Anyone other than that?
39, sir. Sorry.
49.
39, sir.
39. Yeah, 39. Yeah, Padmavati. You are present. I gave you attendance. Yeah. Anyone else? Okay then. Whatever this I'll update in the LMS now. Okay, thank you for joining. Fourth period you join. What is that? Thermodynamics, because he's having invigilation. That's why we just shifted. So fourth period he will take. Thanks for joining. We'll meet tomorrow. I won't be there, so someone else will take. Because I'm going out tomorrow. Then we'll meet on Thursday, right? Thursday during the regular class. I think is it no Friday. Friday also is online. Okay, we'll meet on the online. Try to finish off the syllabus of that parallel series reaction. Thanks for joining. I'll stop the sharing now. Thank you.